Dr. Sujata Ramdorai. Welcome, madam.
Thank you.
She has a very long CV, but I am just because we are also running short of time, I will be speaking very briefly about her important awards and prizes. So she had her PhD from Tata Institute of Fundamental Research, Bombay University, and she got the Santi Swarup Bhatnagar Award in 2004 and ICTP Ramanujan Award in 2006. She is a member of National Knowledge Commission from 2007 to 2009 and also was a member of National Innovation Council from 2010 to 2014. Was also a member of Scientific Advisory Council to Prime Minister of India 2008 to 2014. She got the Krieger Nelson Prize in 2021 and was conferred with the Padma Shri in 2023. And today we'll be listening to the art of mathematics. I have requested personally to speak to our young girls about her journey as a scientist for a few minutes. Then she will be speaking about her work. And before that, I will request our Chancellor. Chancellor, sir, are you there, sir? So maybe there will be little amount of problem in connecting with the Zoom. Normally, madam, we do it in Microsoft Teams. So
yeah, I understand.
Maybe anyway, so if she will be joining, we can have. Now I will request today's speaker, Madam Sujata Ramdorai to kindly speak to our young audience. I am also welcoming GSS Sastri to whom I could connect Sujata Ramdorai Madam ji. And with these words, I would again welcome you, Madam. Please.
Yeah. Thank you, Dr. Sharma. Thank you. It's an honor and privilege to be speaking, and especially so when it is focused around women in science. It's going to be difficult to talk about my career and my work in 40 minutes. So, and also my work is a bit technical and this talk is intended for a general audience. So what I'm going to do is sort of talk about math and what attracted me to math. I'll do that, and then maybe in the end we will have time for questions and interactions, which I believe are more important. And I'll ask for your indulgence to switch off the video because otherwise the voice quality will go down.
Switch off the video. Okay, madam. Yes. Okay.
Okay. So mathematics, it's occupied an exalted position since antiquity from many civilizations, in fact, not just in India. But there is this famous 5th century BC quote which people like to talk about. This is from one of their treatises on astronomy, Vedanta Jyotisha. And it says, like the crest of the peacock and the jewel on the hood of the serpent, so is mathematics at the head of all knowledge. So we knew it already in the 5th century BC, and many other civilizations knew it as well. Then and later, the Western civilization echoed the same thoughts. And Galileo Galilei in the 16th century, he said, learn math, for that's the language in which God has written the universe. Philosophy is written in that very great book, which continually lies before our eyes, by which I mean the universe. But we cannot understand it if we do not first learn the language and understand the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without the aid of which it is impossible to understand a word of it, without which one wanders vainly through a dark labyrinth. And as we progress in technology and in modern science, it's becoming increasingly clear how mathematics in one way or the other underpins the very progress in most areas of knowledge. And then there's always this other argument, is math an art or science? Personally, I would argue that it is a bit of both. It is an art because it has a very creative side. There is an intuition, you have to have imagination, and then you're constantly challenged, and it's not reproducing the same thing again. It has to be something new, there has to be a new idea as the discovery flows and so on. But it is also science because it is what underpins the rigor. Science, as we know, is not just empty statements. Science has to be statements which hold out over time. So there has to be rigor in science, and it's a mathematical language, as Galileo said, which underpins this rigorous side of science, and it's also the language of science, as Galileo rightly said. And in fact, it's perhaps for this reason that even today, in Cambridge University, United Kingdom, a degree in math is always called a BA in math. We say Bachelor of Science, Mathematics, but they still say BA in math, Masters, MA in math. And what I'm going to do in my talk today is give a couple of examples to a vast general audience so that they understand how math works or how a mathematician grapples with math in his or her everyday work. So one of the key things in mathematics is you have to make an assertion, or what I'll call a statement, and it can be a true or a false statement. But if you make a statement and you don't know whether it's true or false, then you have to prove that it is true. And one way of proving this statement is true is by what is called the method of contradiction. So proofs play a central role in mathematics. And in order to prove statements, you rely on previous statements which you know are true. And most of these statements are usually abstract. And you use abstract ideas. In that sense, it's the very opposite of what you're doing in a physics lab or in a chemistry lab, where you mix two compounds and you see that what is supposed to happen is really happening in front of your eyes. Or in physics, when you make measurements and then it matches whatever the formula predicts it to be and so on. In mathematics, it's really abstraction. You're dealing with abstract concepts, but yet you use logic and other previously known statements to further knowledge, again, largely through abstraction. So let me take this statement. There are infinitely many prime numbers. I'm assuming that everybody knows what a prime number is. Prime numbers are those
Madam,
first. Yeah.
sorry to interrupt. We are in the first slide, madam. Are
Oh,
you? Uh,
oh gosh, that's very strange. I mean, this is the first slide. Can you see the
the
next slide?
the art of math, Sujata Ramdurai. That is the slide that is visible on the screen.
Oh gosh, you can't see all these slides. I don't know why you can't see it.
No, other slides we are not able to see. So kindly share it.
But
Now
I
it is
have,
okay. Now math in history. Yes.
okay. But let me make it full screen and then tell me if you can see it. Can you see it now?
Yes, madam.
And now
Now
I'm
math,
going,
no, math in history we are only able to see.
right. And now, can you see this? Is math an art or science?
No.
Oh, okay. So each time I'll have to go back and then, all right. So what I'll do is,
Now is math an art of science. Yes, that is what.
okay. So I'll just increase the size here. I don't know why the full screen is not working. So yeah, okay. You can see this, right?
Yes, yes.
Okay. So this is roughly what I was talking about. And so we are now talking about statements in mathematics and proofs. And let's take for an example, let's take this statement. There are infinitely many prime numbers. And I'm hoping that all of you know what prime numbers are. Prime numbers are those numbers larger than 1. 1 is not considered to be a prime number. You take a number which is larger than 1 and which you cannot write as a product of smaller numbers. Such a number is called prime number. For example, 2 is the smallest prime number, 3 is a prime number, 6 is not a prime number because 6 can be written as 2 times 3 and so on. Now, the statement is that there are infinitely many prime numbers, and this was known already 3,000 years back. It was recorded. I'm sure many civilizations knew this, but maybe they didn't record it the way Euclid did. So this is called one of the fundamental statements in arithmetic. There are infinitely many prime numbers. Now, how does one prove this? So you can keep going 1, 2, 3 and keep checking whether something is a prime number or not a prime number. But as the numbers get larger, how are you going to even check whether something is a prime number or not? So this requires sophisticated methods to check whether large numbers are prime numbers. And again, all this can be done. We know how to do it. And this largely evolved due to abstraction. Today, computers can check very fast. Even your mobile phone can check very fast if a given number is a prime number or not. But how did the mobile phone get to this stage? It was due to the work of pure mathematicians who work with abstract concept and abstract ideas. But let's come back to this statement that there are infinitely many prime numbers, and the proof, this is by a method which is called contradiction. And the idea in this method of proving a statement is you say, okay, I want to prove this statement. Suppose that the statement is wrong. And then you use other true statements to arrive at a conclusion which is patently false, which you can see is false or absurd. So then you make a conclusion, okay, all this is happening because the original statement that I started with is wrong. So therefore, I made the contrary of the statement that I was supposed to prove, which was wrong. So therefore, the original statement is true. So here in this example, we want to prove that there are infinitely many prime numbers. So we make the opposite assumption. So let's assume that this statement is not true. Yes, okay, somebody's raised a hand. Hello?
Madam Priyambada, madam, have you raised the hand?
Maybe we can go to questions at the end. Let me finish
Yes,
this.
yes.
Yeah.
Yes, madam. Yes. That will be better. Yes.
Yeah. So one assumes that this is not correct. So which means that the opposite is true, which means there are only finitely many prime numbers. So one assumes that this statement is not true, which amounts to saying that there are only finitely many prime numbers. Then we use this to get a statement which is obviously absurd. So one concludes that this is happening because our assumption that the statement is not true is wrong. So therefore, this statement has to be correct. So this is called a proof by contradiction, and this is one of the oldest methods of proving such a statement. Oh God, now I just don't know why this is happening. Not able to move to the next slide. Okay. So now to prove this particular statement, we use what's called the fundamental theorem of arithmetic, which was proved by Euclid, which is, you can notice, it's 3rd century BC. So mathematics has a very long shelf life. We still use this result, which was proved 3000 years back. I mean, this is the first time it was recorded. This must have been known to civilizations even before this. So what you do is you assume that there are only finitely many prime numbers. Then we are going to use this fundamental theorem of arithmetic, which states the following. Every positive integer greater than 1 can be written uniquely as a product of powers of prime numbers. We know this. 6 can be written as 2 times 3. 15 can be written as 3 times 5. 8 can be written as 2 into 2 into 2, 2 cubed. 12 can be written as 3 into 4, which is 3 into 2 squared, and so on. So we use this fact. So now suppose we are assuming that there are only finitely many prime numbers, and let these be the finitely many prime numbers, P1, P2 up to Pk. Now I take this number, I multiply all these numbers, P1, P2 up to Pk, and add 1. I'm sorry, there's an exclamation mark here, but it should be 1. So you add 1 to the product of these prime numbers. So then you show, now you take this number n, and then you show that this, by the fundamental theorem of arithmetic, n should also be expressed as a product of prime powers. But then you show that this is not possible because of the form of this number. It is the product of the finitely many prime numbers, and you have added 1 to it. And then you show that this number is not a product of finitely many prime numbers. So therefore, but Euclid's statement is correct. So therefore, this is contradicting Euclid's theorem, which is a true statement. So our initial hypothesis was wrong, so that we cannot say that there are only finitely many prime numbers, and so we conclude that there are infinitely many prime numbers. So that's the simplest example of how proof by contradiction works in mathematics. Now, guided by intuition, mathematicians make statements which they feel must be true. And this is where the question of whether it is art or science comes in. If it were pure science, then you wouldn't even be allowed to make a statement like that or guess something without having some evidence. But mathematicians often are guided by intuition. They might have very scanty evidence, but still will be bold enough to make statements saying, oh, I believe this statement. I cannot prove it, and but I believe it's true. And such statements are called conjectures. And there are many conjectures, especially in number theory, which are easy to state but have not been proved for many centuries. So I'll give you a simple example here. One such example was made, one such conjecture, one such statement was made by Christian Goldbach, and it's called Goldbach's conjecture. It was made in 1742. So it's close to, 300. It will soon be 300 years old. And there's not much progress in this. But we don't have any evidence to show that this statement is wrong. Everybody believes it, but there is no general proof available. So this is the statement, Goldbach's conjecture. Every even positive integer greater than 2 is a sum of two prime numbers. So take any positive integer which is greater than 2. Then the statement says that it has to be a sum of two prime numbers. So 6 is, we can write 6 as 3 plus 3 clearly. 18 is 11 plus 7. But these are small numbers and you can figure out. But what if I give you a number with a million digits long? We still know that it has to be, the statement, if it is true, it says it still has to be a sum of two prime numbers. But now if you're taking a number with a million digits, and if you're writing it as a sum of two numbers, then those two numbers should also be very big. And how do you know that those big numbers are prime numbers? Fortunately, we have methods today which allow us to check that a given number is a prime number. But this has to be done with the use of computers because you want a fast answer. So you input this number into the machine, and then there is an algorithm. But that has nothing to do with the computer. It's not because of the computer. What the computer does is just quickly goes through the steps. But that algorithm is based purely on pure abstract mathematics, which was the work of mathematicians for over 300 years. So this again gives you an idea, I hope, of how mathematics works. It leads to advances in mathematics again by way of development of new areas. You want to prove a certain statement, and as you are trying to solve that problem or trying to prove that statement, you give rise to newer areas of mathematics. So typically, while trying to prove conjectures, new areas of mathematics evolve. And these areas themselves come with new problems. In turn, they will generate new conjectures, new problems, and you have to develop new techniques. And this is how new areas of mathematics evolve. So this was one thing that attracted me to mathematics from a very young age. The fact that you just had to understand and then logically argue. Whereas in most other subjects, apart from understanding concepts, let's say even in a subject like physics, apart from understanding concepts, there were certain things you had to do by hand or observe and so on. Whereas in mathematics, if you understood the concept and you had to argue logically and then through abstract ideas. So this component of abstraction really played a role in me choosing math for my higher education as well. And in fact, at that time, it was engineering which was becoming very popular. And I was torn whether I wanted to do computer science or mathematics. And then I had a senior person in college, and he asked me, do you like working with your hands or do you like thinking abstractly as in mathematics? I said, oh, no doubt, I like thinking abstractly as in mathematics. And he said, then don't do engineering, just do mathematics. And it's kind of funny today, we have come full circle, even in technology or in engineering. We are talking about artificial intelligence, machine learning, and all of this use mathematical ideas, use the language of abstraction. So these areas, as you are trying to solve conjectures, new areas of mathematics develop. And then this, according to me, adds to the beauty of mathematics. So that's why I would argue that there is a component of math which is art. But yet, this conjecture, even though you know it to be true for huge numbers, but it is still considered open because you have not given a general proof. What you can do is give me a number, any, however big it is, and then I can try and find two prime numbers such that that number is a sum of two prime numbers. And then I'll use deep ideas to show that these big numbers are prime numbers and so on. So that's already adding a lot of layers of difficult mathematics. But even after all that, nobody will say Goldbach's conjecture is proved, because Goldbach's conjecture has to be proven in complete generality. You cannot take one single number and say, look, I can do this for this number, so therefore it must be true. So this is another aspect of mathematics. Not just, this maybe one can say that this is true more generally for other areas of mathematics as well. For instance, you can take physics. Physics also, people do a lot of guessing, but in theoretical physics, you have this other component of experimental physics, where something predicted by theory is checked or verified experimentally. And along the way, when things are done experimentally, they come up with huge amounts of data, they see patterns, and then they try to understand, why is this happening? Can we build a theory to explain why this is happening? And as we all know, this theory keeps getting revised. Newton started with his theory, which worked for big bodies. But later on, once the quantum phenomenon was discovered, you had to come up with quantum physics and subatomic physics and so on. And today, we still don't understand many things in the universe. So you have string theory, you have cosmology, and all of that. But the interesting thing is to ultimately prove things or to even make conjectures in these areas, even trying and understanding various phenomena. Even the physicists have to use the language of mathematics. And that's another remarkable thing about mathematics. For instance, in string theory, the physicists are using mathematics which was proven by mathematicians 200 years or 150 years back, not ever thinking that one day the physicists will need this for their work. So that was another side of mathematics which really attracted me, the longevity of it, that you're still, the ideas and proofs and theorems which were proved thousands of years ago are still used. And so for me, the underlying melody for the harmony in math is abstraction combined with rigor. Now, what I'm going to do is close with two images. So while math can be construed as art, there is also the math of art. Math can generate art. In what sense? There are all these very beautiful images. I'll just show you two images as a sample, but there are many of them. You can Google art and math and you can come up with various images on the internet. And then if you really want to understand the mathematics underneath it, you'll see that it runs to mathematics that's covering a long period of time, let's say 300, 400 years. One of them, it can also be the other way. And so this is one example. This is a fractal. I'm sure many people have seen fractals. People have at least heard the word. Now, there is a mathematical theory of fractals. So you need mathematics to, this is now fractals can be considered as it's a separate branch within mathematics. And then you can use mathematics to understand fractals, what's happening. And then you can also use mathematics to generate more fractals using computers. And this one is a little more complicated. This one is called the fundamental domain of fundamental domains on the upper half plane. This requires tremendously sophisticated mathematics, starting with the real line. You all know that the real line can just be thought of as one straight line with zero in the middle and going to plus infinity on one end and minus infinity on one end. And then we also work with the complex plane, which is two real lines. So for instance, you can think of this page, and then you draw the x-axis and y-axis. Most of us study this in the high school. That's the plane. That's two-dimensional because you have two real lines. Now, in this, you just consider the upper half plane, which means all the part of the plane above the x-axis. So you have the x equals 0, the x-axis, you look at the upper half plane. Then you have various other interesting mathematical objects called matrices, 2 by 2 matrices acting on that upper half plane. And you can use that, you can study the action and then come up with very deep, sophisticated theory which will help you generate such images. So there is the art of math, there's also the math of art. And for those of you who are interested, you can Google more, read about it, and so on. And I hope I have convinced you in this brief session why mathematics appeal to me and why there's an aesthetic side, yet the aesthetics does not compromise on the rigor, which is the key feature of mathematics. So I'll stop now because I think we got a message saying that the meeting will end in 10 minutes, and I'll be happy to take questions. Thank you.
Thank you, madam. Thank you very much. Uh, why mathematics actually attracted you to make a career in mathematics? Very nicely explained. I think we'll take two questions because as such the room is going to be closed within 10 minutes. So now we're open for questions. Any questions you can ask here? Anybody?
You can also ask questions on the chat if that's easy for people.
So you can use the chat also. Sir, madam, what is the mathematics behind these fractals?
What explains this symmetry, right? I mean, there is a certain symmetry. It's endlessly repeated, right? It's endless repetition, and you take any part around that and compare it to the larger part, it looks identical. If I zoom in at this part, then it will look like this larger image that you're seeing. Right?
So it's an infinite repetition of the same
Exactly.
pattern.
Well, infinite repetition, what we would like to say. So what you're doing is you're focusing, you're zooming in at some part. Then after you amplify it, it's looking that like an image in some other part. So this is what in mathematics language, mathematical parlance, we would say homogeneous. And this is a concept which we know, which is a mathematical concept. So you try to understand fractals through that. Now, what you can do today, there are computer programs where you can use mathematical equations to generate fractals by varying parameters. And such programs typically use abstract mathematics. Again, if people are interested, there's a nice article on Wikipedia itself, I think. So if you look at the math behind fractals, you can read a
Fractals.
lot more.
Okay. Thank you, madam. Yes, you can ask your question.
हेडचे पच्चीस रखिजो
Yes, please ask your question.
Myself,
Yeah. I can't hear you. Maybe somebody else can. There's a nice.
You switch off that one, and I think it will catch the. Yeah, you can
why
speak
don't
from
you
there.
why don't you
Switch.
put it in the chat box? Put your question on the chat box, if that helps.
Or you can speak here.
Good evening, ma'am.
Is it audible, madam?
Okay. Yeah, now you're audible. Yeah, go ahead. Yeah.
Yes.
Myself, Chitraliti Nayak, ma'am, and my question for you is, what is the relation between arithmetic and geometry, and which one is more fundamental?
If you ask somebody who's working in geometry, they'll say geometry. If you ask somebody who's working in arithmetic, they'll say arithmetic. But at a very basic level, you can't say that there is something connected. But let me give you a very simple example. In geometry, take a right angle triangle. You all know Pythagoras theorem. It's called Pythagoras theorem, but several civilizations knew it before Pythagoras. right? Do you know Pythagoras theorem? Take a right angle triangle, then square of the length of the base and the square of the height is equal to the square of the hypotenuse. Now, suppose my base is 1 centimeter and the height is 1 centimeter. Then what is the length of the hypotenuse? Square root of 2, right?
Square root of 2.
Now, for a long time, for hundreds of years, different civilizations couldn't understand square root of 2 because it's not a natural number, it's an irrational number. There are rational numbers. Do you know rational numbers? Rational numbers are basically fractions. Irrational numbers, you cannot express them as a fraction. And if you express it in terms of decimals, you won't see a pattern in the decimal. It will just go on and on and on and on and on, and you won't see a pattern. So square root of 2 is an irrational number, but it comes up in geometry, right? This is one of the simplest connections. And then there's also this golden ratio. You can read more about it in Google the internet. You'll read more about it. It's again an irrational number, golden ratio, but it plays a very important role in different areas, in art, in architecture, and in music. So it's something very appealing. Wherever you find a golden ratio, majority of the people will say, oh, that's nice. If it's a building, or you can make measurements, and in the face, again, you can read about it in the internet. Just look at golden ratio and aesthetics. So this golden ratio is a number, but it again shows up in different aspects of geometry, art, architecture, and so on. Okay, there's one question in the chat. Nice to hear how to move this topic to school level. Again, I mean, today, we all grew up in an era of poverty of knowledge. Today, the problem is there's a plenty of knowledge, and so there's information overload, so nobody is interested in anything. Shastri can tell you, in an area where there was nothing, he created everything with his hands, whether it was making models of insects or origami and so on. Just go to the internet and look at art and math. You will come up with various YouTube videos on how you can introduce various things to do with your hands in school, for school, high school children, and how you can explain mathematics through that. Okay, so there are lots of projects which you can already start in secondary school or in high school. Okay, how can understanding, ma'am, what are the methodologies we can use to solve Goldbach's conjecture? Okay, that's a difficult question. First of all, like I said, one important thing is to say, how do I know that a number is a prime number? If I take a very big number, how do I test whether that number is a prime number? So this is called primality testing. That's a separate branch by its own. You obviously have to use that. And then you use other methods in number theory, which is a bit technical and difficult for me to talk about it. But again, some of the things, if you want a broad overview, you look up Goldbach's conjecture on Wikipedia. That article is pretty good. You can read it. Okay. And then there's another question. How can understanding mathematical principles enhance creative problem solving and innovation in artistic fields such as visual arts, music, and design? So again, go read about the golden ratio and how it comes up in all of these that you're saying, visual arts, music, and design. So once people learn, hey, there's something which is purely math. I'm not saying that just because you know the golden ratio is there, you can become a better musician or a better artist and so on. But this appreciation that mathematics is somehow intrinsic, hopefully that will not scare you away from mathematics. It will lead you to deeper exploration. And then it will lead you to a deeper understanding. Let's take the architecture of an arch. You've seen an arch, right? So underlying the arch, the construction of the arch is trigonometry. Now, when you teach students trigonometry, they don't ever relate that trigonometry is related to what you're seeing in real life. They think that they're just being tortured, learning about sine
But
theta.
there is only 1 minute, less than 1 minute left. So there are many more questions also. There is a question in the chat box. So
okay. There's one more question. Is this fractal same as pattern shown in Emperor's New Mind? Not really. Not this fractal same as a pattern. I don't know. I haven't seen this book, Emperor's New Mind. You can just ask for fractals and Google will give you many of them. And I chose one which I liked. what?
Oration, and the next SOAFAL oration is on 30th, 30th, 13th July, and we'll have another. Uh, good evening, sir. Good evening, Excellency. And we'll have a, because this was actually done in Zoom, and we don't have a Zoom license. So the meeting was completed in 45 minutes. Next SOFAL lecture, we'll do it in the as usual in the Microsoft Teams, and then we can have more question answer and discussions. Because today's speaker is in British Columbia, Canada, and their university doesn't allow the use of the Microsoft Teams. So it was blocked spontaneously, and that's why we have to go for the Zoom link. So, on behalf of the university and the outreach cell, I am extremely thankful and grateful to His Excellency and all the privileged and all the dignitaries and the participants. So, we'll see you in the 81st SOFAL oration or the 6th SOFAL 4 series oration on 13th July, the same time, with another Lilavati's daughters, Tanushree, Professor Dr. Tanushree Das Gupta. With these words, today's meeting is closed. Thank you very much.